Okay, everyone. I'm Samandi Silva, as you know. Probably I'm meeting you for the first time. So, hi to you all. The way we have about 3 hours to discuss a few things. Um, the way that we will spend this weekend is I'll spend about 3 hours with you today here. The session being recorded. And I will probably, we are supposed to give breaks because you can't have long term concentration on online teaching. So we were supposed to give reasonable number of breaks. So my thinking is I'll try and do it in 1 hour segments with about 15 minutes break. And we will proceed with that. So today's this is a common lecture, obviously, as you may be aware. But tomorrow we will be having our design workshops. In that, what I will be doing is I am taking the morning session. You don't have to attend both sessions. You have to only attend one session. If you're, I have put an announcement. If you're doing units A and B, and then you will be, you can join us in the morning session. And then if you are doing C and D units, then you can come to the afternoon session to the workshop. That is for tomorrow. So I'll take you through general information. Some of them, of course, you may know by now because you are in halfway through the semester. Hopefully, you must have started your project work. As you all know, this is a fully project-based course, which means you learn by doing your main project. But at the same time, today's time, I will explain to you basic um, things which you require to know when we talk about the green building fundamentals, achieving sustainable building stock. In this case, we will be talking about residential buildings. So you will be doing your own units being designed internally. And then we're trying to do a interior layout which we can justify as a sustainable interior design. And then secondly, we will try to implement what we call the design for deconstruction policy, or rather I would say design for deconstruction and reuse. um, Traditionally we were what we were doing was we designed for construction, not designed for deconstruction in mind. So it's a philosophical change in design for the future. Um, the advantage of that is that some of these or parts can be recycled rather than sending it to landfills. And this is probably one of the early involvement of you guys as students to understand what is this all about. Then I will get into the project as we go. Okay. So when you're talking about green buildings, there are a lot involved in it, as you all know. Probably you may have learned it in other subjects as well. My focus is basically how we can actually do a really sustainable building stock in any country, in any city, by applying certain set of principles at the design stage. So that is the focus of my discussion today with you all. Obviously, it is almost a common practice now. Solar energy is either produced through the solar cells in a house. setting or in a building setting, or at the same time, you can use what we call a set of passive design principles. If you do your interior designs according to those principles, we will discuss a little bit later in detail, then you would know that it will have far less energy consumption for cooling or heating. In your case, most of the time it is cooling in Hong Kong situation, but in Australian situation now we are um, going through the winter. In this time of the, it is more of heating energy we will be saving if we do it properly. So the uh, passive design principles here refers to um, uh, how you can actually use the orientation of your building, and then you're providing the windows in the right areas or sides, um, whether it is to east or north, depending on which part of the world that you are living in. But you can harness the power of sun when it is cold periods of the year, and then sometimes it can be um, in your case in particular, what you would like to see is not to face your windows and other things straight into the west side sun, because it will be very warm. So uh, solar energy therefore can acquire or keep out when not necessary through what we call passive design principles. But on the other hand, um, you can use it for to create a very beautiful interior comfort within a house, where actually the energy is less used, in your case air conditioning. um, the other one, other aspect of sustainable building design is more and more the material which we use for civil engineering, particularly in the building industry. We are trying to see whether we can minimize the embodied energy of the material. Here, the embodied energy refers to the amount of energy you require to produce that particular material. Let's say a concrete, you have 1 meter cube of concrete. You can estimate what sort of, how much of energy it requires to produce at a batching plant, and then brought it to site and placed in your particular building. So that particular amount of energy is for the production, transportation, harnessing the materials. Say, for an example, how much of energy would require to um, uh, produce the cement for the start, and then of course fine aggregates and coarse aggregates, and then mix it and then transport it to site and place it. There are These are not done by civil engineers, but there are people who are doing this and then calculating what we call the embodied energy. Everything you have, what you wear, what you use, where you live, has an amount of energy which is embodied, already absorbed in that particular product. So your pencils, your books, when you travel, shoes, your clothes, everything will have that. So if we are to be serious about sustainability, we have to try and find ways of smart production and materials which are having lower embodied energy in it. So that is one of the other aspects. So when it comes to real energy, um, when you're looking at your residential building, say for an example, that those are coming from two parts. One is actually the embodied energy. The other one comes from the what we call operational energy, which means you're switching on your light, you're using your computer at a given time. Now that energy is what we call the operational energy. But the embodied energy is a constant kind of a thing when you do a building. So nowadays you can actually really calculate these things reasonably accurately. It is not a perfected science, but it can be calculated very reasonably nowadays, which we didn't do that long time back. So that's an interesting new thing for the young engineers like you are. And of course, the other thing is we all know how important the water is, and particularly in Hong Kong situation, you all are living in high-rise buildings, mostly housing so many number of units in it. And then what does that mean is that the water consumption and water saving, uh, harnessing the rainwater, either as a collectively or as a building by building in your case, or some well coordinated system to collect the rainwater and then harness it and put it back to use, is another area. In Australian conditions, we are living in a much drier country. Hong Kong is having very good rainfall, being very close to the coast, as well as and mostly island, and it is Hong Kong receives much more water in volume compared to Melbourne and Australia. But here, what we are trying to do is, because water is very scarce, so we had to be very careful with water. And then in particular, what we call it, generally when you're looking at water, you have to categorize them, of course, because what we call potable water is what you would be drinking, the quality of drinking water. And we are trying to optimize or minimize the potable water consumption. And also we like to supplement other things like, say, gardening and washing your cars and things like that using different types of water. So we have potable water, we have rainwater which can harness, the other one which we call grey water recycling. Grey water here refers to as the water which is used in your showers, and then what you are using in your washing machines can be treated, and then uh, normal wash basins can be considered as grey water. This water can be collected from your household and refined sorry, locally, and then it can be used. In Australia, we are now doing it reasonably well in new houses in particular. Designed for improved indoor environment and air quality is a major concern is most of the sustainable designs nowadays. Air quality depending on, of course, the situation is slightly different. For an example, again, if I go to Hong Kong situation, air quality sometimes really good. Sometimes it can be not that good because of the number of vehicles and then the condensed way of living in Hong Kong, very high density population in the city, and then you are living in tall buildings most of the time, so the air quality situation can be a major issue. So when we are talking about green buildings, it does not necessarily environmental sustainability as well. It is also actually the health of the occupant as well. So as we all know, what we are going through now in the COVID situation, it is very relevant to discuss how the air quality within a building should be controlled. Now, one of the major findings is that in a tall building environment, this recycling process, internal recycling of air through the air conditioners and other things, can have a higher probability of infections. So these are the things that we will learn from this type of experience and from unfortunate situation we are in at the moment. But what we are trying to do is in the future, it will be very seriously taken into consideration how the future buildings, particularly air circulation within the building, will be looked at. A lot of research will go on in next few years to try and find out proper solutions so that the people will not get sick. Even if you people get sick, and it will not spread fast inside your home area, which is basically in your case is a multi-story high density living in some parts. fundamentally, some of the people, when you're talking about the green building, they talk about the minimizing the or neutralizing the carbon footprint of your design home. How it can be done, everything, as I said, what you are using, the energy or your embodied energy within the building or the embodied energy per person, if we can reduce or be careful about, and then that will become a less carbon footprint in your situation. So how can we design a house? At least there's no way that you cannot completely avoid the use of energy, but what we are trying to do is to conserve them as best as we can. So energy wise, if you design a building, as I said before, has three types of energy types which we consume. One is called the embodied energy, fundamentally energy of construction, structural materials, finishes, services, white goods, which means what you put inside your kitchen areas and things like that. So every material you see around in the construction industry will have certain proportion of embodied energy. Nowadays, you can actually calculate embodied energy reasonably because data is becoming available. Again, it is not a perfected science, but it gives a very good indication, which I will discuss a little bit later. So, for an example, we used to have bricks which were burnt in furnaces, which had enormous amount of energy and carbon print at that time. Nowadays, you don't see those type of bricks, kiln dried bricks. Nowadays, you have quite a number of different products coming into the marketplace, which are far better than the burnt bricks which we used in most of the time. So that is a classic example of embodied energy, to minimize the embodied energy. Operational energy, you and I know very well. Every time you put your switches at home, you're using your computer, there's a certain amount of energy being used and utilized, and that is called the operational energy. That you can again save, you can try and minimize it as well. There are a lot of products and then a lot of knowledge has been gathered over the last 10 to 15 years to try and actually minimize operational energy as well. In particular, interest is, as you all know, photovoltaic, which is solar power panels, solar power being harnessed in almost every conceivable way to minimize the energy side of things. Recurrence energy is, say, for an example, if you have a building, office building or residential building, what you require is time to time you have to maintain it. It will cost some energy. If anything costs money, it will cost energy as well. It is pretty much correlated in a way. So if you take your replacement, repainting, or maintenance, or any improvement, any advancement in lifestyle, for an example, all associated with the recurrence energy of a structure. In this particular, I'll be uploading these slides if I have not already done it. I'm pretty sure that I have done it, but I'll double check whether it is in Canvas. Embodied energy there is a very specific definition for embodied energy, guys. So, which basically means that there are two types. One is called cradle to gate. In this particular subject, we are not calculating in a sense. This is one of the areas if you are doing your capstone project, say for an example, in your next year, and then you will find this area is pretty good for research. How actually this happens. This will become more and more important over the time as the time goes, particularly when you guys are at the future, and then understanding of this embodied energy and operational energy and how to minimize that will become very important um, responsibility of the society as we go. So there are two types we are talking about. I don't want to go too deep into this one, but cradle to gate means that um, when a raw material is identified, let's say timber, it is normally a natural product. It is carbon negative. It does not cost any energy. In fact, it is producing oxygen. It is a better product. But that is the natural tree which we are talking about. But however, if that was to be felled and then converted into construction timber, a timber which we use in the construction for various types, then that will start to add energy added onto it. You have to fell the tree, you have to take it to a mill and then saw it to planks, and then you have to make it to sizes, transport it to the site, and all that energy will then slowly start to make it a carbon positive or energy positive, um, having a carbon footprint greater. But it is supposed to be a carbon negative product as a natural product. However, we can't say the same thing about any mined material. Say, for an example, cement. Cement has a huge amount of embodied energy for a number of reasons. Of course, first, its raw material has to be harnessed from somewhere. It has to be mined and bring into a factory, and then you have to grind it. You have to make it a very fine powder, and then that requires energy. So energy, carbon negative product as timber, whereas cement is from the beginning it is a carbon positive. So say for an example, cement industry has done a lot of research and then improved their products so much now. There are a lot of savings, but it is still, we are not saying that you cannot, we know that we cannot live without cement and cementitious materials because that's the main construction material we know. However, you can make it a little bit better in terms of carbon footprint. So there are two types of embodied energy as we discuss here. One is coming from the original raw material up to the production and coming out of the manufacturing yard. But then it has to be transported, then it will be used into construction, and then construction means then you have to actually have some admixes and various other material added onto it, and then when it becomes concrete, it is a combination of cement carbon footprint plus the fine aggregates plus the coarse aggregates plus the various type of agents that we are putting into make concrete workable. Say for an example, AI and training agents, and various type of admixtures which you put into this type of material. The cradle to site is therefore so cradle to gate, and then that is a production by itself. But when it is put into practice to build, and then it will become cradle to site situation, and then these embodied energy will remain there as embodied energy. And then if you were to really look at the overall picture, this only talks about part, because then once it has to be demolished, it has to be recycled, or it will be put on the landfills. So there are two aspects in sustainability is very important. One is the landfill, the material, and the other one is the embodied energy component of it. So this is a typical Australian single dwelling house. We can estimate the embodied energy component in external walls, internal walls, roof, paints, how much it goes to staircases, how much it goes to doors and windows and so forth. We as engineers don't do this calculation, but nowadays the data is available. So if you wanted to do a full life cycle analysis of energy consumption in a building, you can actually reasonably accurately do that. These values are varying from practice to practice, country to country, totally different. For an example, in typically Australian, most of the Australian houses, unlike in Hong Kong, are made out of timber as a material. Structural material is timber. And then in that sense, Australian houses are, you can say per person, per capita, it has a lesser amount. But you can't say that because we are living in large houses, relatively large houses in Australia, whereas Hong Kong, a lot of people live in small. So the per square meter, how many person per square meter or size of a house is totally different. So in the other way, that Australians are consuming more in a domestic sense in dwellings, has more energy footprint because of the size of the house per person. Here, normally a standard house would be in the modern day now around 25 squares, which is 250 square meters, to about 30, 40 squares, which means about 400 square meters, which is really, really large for about 4 people or 5 people families. Whereas in Hong Kong situation is slightly different. But unfortunately, in your situation, what happens is that it will be in large housing or high-rise residential buildings, so it will have a completely different footprint. The fundamental point which I wanted to say here is that we can actually calculate all these things reasonably accurately. It is not perfected science, but it can be estimated to get a feel for it. Why is this type of information is important to the future? Because you can see in this particular diagram, pie chart, I would say, our external walls in Australian setting, our external walls have large proportion of 42% of the total embodied energy or energy consumed. These are not operational energy. We are talking about embodied energy. You have to add on to this one operational energy, which is everyday electricity, which we use for the winter heating, or for cooking and washing and all that sort of stuff. But the important factor is that we can estimate them. We can estimate and then we proportionately see. And then if you're an Australian person who is really worrying about wanting to make some change, they'll say, hey, okay, external walls are very energy intense. Why is that? If you say that because we used to have burnt bricks as the facade, which is outside of I think our structural load carrying members are timber, but we, as the facade outer look, we have pointed brickwork in most of the things, and then this brickwork is normally kiln dried or oven dried bricks, which means they are having a very large carbon footprint. Okay, so that is one of the reasons. Now, however, the industry has gone, and then very rarely we have now kiln dried bricks. These are mainly either dried by through ventilation. We don't put it into an oven or a kiln, used to call it. So that we have relatively better timber, bricks available now. But overall, that is how any product, if you identify that carbon footprint is greater, energy consumption is greater, then we can tell that particular industry, can you kindly look into how to improve this particular carbon footprint? And then by doing that, it will give a better positioning in a sense. So this is I'm showing to most of my students, just to give you a very quick snapshot of what is embodied energy and what is carbon neutrality. If you look at this one, these both products are carbon neutral or carbon negative. products. But if you look at the two stickers stitched on that, it has carbon footprint in that. It is just a comparison in overall sense. Sometimes we don't think about these things. Say any packaging, for an example, will have. So we have to try and improve the practices because we took a lot of things into grant. That's why it happens. This is an example which is called BE. This was developed by one of my master's students some time back. We all know in any engineering project, we have what we call the bill of quantities, which means we know what is required for that particular construction or building for engineering project, and then that can be carefully cost in every contract. You will be having the cost estimation. So the argument was we have done this in quite some time back, but the argument is, what if that with the bill of quantities that you have another column, and in which we are able to calculate how much of energy that consumes a particular product. That is the last column, if you can see to your right hand side, that is embodied energy. So if you can compare all the activities we are doing here, this is a typical residential building that graph came from. So we would be able to identify how many gigajoules of energy being used to construct a house. And we also can see how much of cost would involve in constructing that house. So dollar value versus the energy footprint. And in that is a good way, in a way. Just imagine that one day we can actually minimize the cost, both cost and the embodied energy component. That will be fantastic. But this is how the research side of work is happening at the moment in this sector. So I will go from that energy consumption and conservation aspect for green building aspect. So that was the embodied energy. Now let's have a quick look at operational energy efficiency. Of course, there are a number of steps we can do. One is actually use the passive design principles to have a thermal comfort within your house, without mechanical ventilation or air conditioning or heating. There are a lot of products nowadays, a lot of research is happening in this area, a lot of products being coming into play to try and bring down the energy consumption of the products. So passive design principles are a set of rules. It varies depending on which country that you are. Say, for an example, Hong Kong is very similar to Sydney in Australia, weather-wise. But if you look at Melbourne, where I am sitting now, and in the Melbourne winter is relatively colder. So because of that, our heating cost goes up. But if I design a house using what we call this set of principles, passive design principles, which is suitable for Melbourne conditions, I will be having a relatively less energy bill to pay. More importantly, I will be having less energy consumption. So that's what the passive design principles document does. From the your instructions, we have provided you this embodied operational energy component aspect, and how the passive design can help us. We normally in Melbourne situation, you have to orient the building towards the north, particularly the large windows and other things towards the north will give you a better energy outcome, which means a lesser energy bill because you will be relatively using less. I'm not talking about huge values, but basically if everybody chips in, then it will be a saving. So photoval photovoltaic, which is the solar panels, basically. I just mentioned at very early that was the case. You can, which is pretty standard practice now. There will be very few houses now, new houses now left without solar panels on the roof. And then I'm pretty sure in Hong Kong, most of the buildings are trying to um, set examples for the future by engaging uh, the solar energy harnessing systems. So obviously, this is the future. If we can make use of this particular energy generations, not only for your normal thermal comfort within the house or cooking and things, but also just imagine if we can use this one even for charging your solar batteries and then using in your cars, which is in Hong Kong. Most of the cars are, I think, one of the largest cars to population ratio, where the solar system is, and the cars are energized by, of course, the um, solar energy type products. So it is an important aspect. So if the fuel can be saved using electrical cars, then that will help. But where the electrical cars electricity is coming from, if that can be stitched to at least by part to solar, and then that will make it more sense. That will make more sense in that sense. Obviously, most of the housing, but I don't think in Hong Kong situation this is that strict. Thermal insulation in is very important. Ceilings and external walls, uh, uh, which is more applicable into a coldest weather conditions. But in Hong Kong situation, one of the important things in house designs um, are we talk about the cross ventilation aspect of that. So if we can generate a draft, um, um, one the cooler side of your house, and then having doors and interior doors and windows are aligned in such a way towards the warm side, and then you will see that it will, from one end it will suck air at a lower level, and then the heated air will rise up, and then through the louvers it can exit from another point. So if you draw some simple rectangle and then have two outlets, one is at the bottom and one is at the top, and then if you have the warmer side, colder side to the bottom, and then the warmer side into the top opening, and then it will create an internal draft, which will keep the interior thermal comfort pretty good. So that's what you call the cross flow ventilation. And then most of the buildings in Hong Kong is normally uh, uh, decided by that. I may have to draw a couple of lines here, guys, because I think it's in black. It doesn't come. So I'll have a line here, y-axis and x-axis. So this is x-axis, and then this is the operational energy. Um, uh, this one is, let's say, energy consumption. So this one is the time. Say if this is, let's say, t equals, let's say this one is t equals, all right, say draw it. So t equals 0, which means the time that the house is built and somebody has moved into. Let's say this is at 25 years down the track. um, uh, 25 years. So this is time axis, sorry. This is time, say years. So 25 years, this is the time of the building is constructed. These three lines are you can say the very careful uses of energy like electricity or embodied energy or combined embodied and operational energy. Um, this blue line is very carefully energy being used. Um, so they are not that large consumers, but the red line is the people who are actually having too many appliances and not careful with the energy, and then that so they are representing medium, heavy energy consumers, red color, um, and then medium and the lower uh, energy consumed people. Now, this is operational energy. From the day that you occupy the house, this will keep on increasing. It's a cumulative value, which will go until about 50 years. Maybe you can calculate as further as possible. Now, for argument's sake, I will use different color and then I'll draw the embodied energy part. So embodied energy part is at t equals 0, it will be somewhere here, isn't it? So if I draw a line and you can see this line, if I draw, which is the embodied energy component, which is a constant, of course. And then if you want at any given time, if you wanted to see how much of energy being consumed by a particular given facility, what you have to do is you have to combine these two values. Basically, the orange or yellowish color value should be added to either the blue coordinate or the green coordinate or the red coordinate. So for the guy who is um, using highest, you can see when these two energy values, embodied energy, so this value would be embodied energy, which is nearly a constant. Of course, it is not truly a constant. If you repair works done, you make a alteration and things like that, it will come into say energy, basically embodied energy. I'll put a small e there to do that, and then this is the operational energy. These ones, I'll use the red color one here. So this is the energy at a given date of the operational energy. I'll put it as O. And then actually speaking, the at any given time, then these two have to be added together to get overall consumption of the energy of any building or any facility. Does that make sense? Because the E is an embodied, it's a constant. From the day that building is completed, that will be the embodied energy. And then after 25 years of occupation, operational energy will come into play, and whether it is a moderate user or average user or a heavy user, you should be able to work out. Generally speaking, in Australian conditions, it is almost added double by the time of 25 years. 25 years embodied energy and the operational energy are very equal, so you have to add it together. Basically what it means is energy consumed is doubled every 25 years. Every energy means carbon footprint, carbon emissions. So what does that really mean? Every individual household will double its carbon emission uh, around within 25 years. That's and then if you look at the number of population and then you multiply it, you will see that there's a significant contribution of energy, which means greenhouse gases, um, a significant amount. So that was the intention of that thing. Right. You energy rating tools. This is operational energy plus embodied energy. Rating tools have plenty. There are quite a number of softwares nowadays used. I'm pretty sure that you are familiar with LEED, um, uh, which is a very popular and one of the first tools to come into play. The And then the other one, in Australia, we are using one called First Rate, um, which is very pretty much developed and then used in Australia. So there are a number of very well-known energy calculation energy rating tools available. Bream is one thing. Another one, I think, in Hong Kong, Bream is pretty popular. So there are a number of different types of softwares nowadays that you can do what they call life cycle costing. Life cycle costing does not necessarily mean the the residential building part and the um, uh, operational energy component. It has a lot of other things embedded in the in that respect. Life cycle, total life cycle costing, but more importantly, from a building perspective, BREEAM, LEED is the USA one, and BREEAM and First Rate for, I think this is more popular in this part of the world. I think Australia and New Zealand is heavily using this particular software. For this particular subject in Australia, there's a very interesting uh, website which is giving all the residential buildings um, sustainable home design guidelines and then advice and ideas that is called yourhome.gov.au. And also, as engineering students who will become engineers sooner, um, um, Hong Kong is one of the leading people in your part of the world, including Singapore. Residential initiatives and achievements through HK Hong Kong Housing Authority has issued in 2018, 2019, somewhere there, a very good document, and it's a very comprehensive strategic plan for Hong Kong conditions. So, as a student who are studying sustainable infrastructure, I think it was important for you all to know the Hong Kong one as well as your home. If you type these you can easily download the Hong Kong one and your home one is live, so you can go there and have a look how the practices in Australia is there. If you choose to do a little bit of research in this area, these two documents, in particularly for this particular subject, will be very interesting and valuable. Um, So I will just now, that is a general aspect of the sustainability, particularly in energy sense, that we have focused on. We'll now get into the particular major project that you all are doing for this semester. What is expected of you? What it is mean by we are introducing a new word called DFD, which is design for deconstruction. You can consider it as some people name it as design for demolition. I think it is better design for deconstruction would be a pretty good one on a positive note. So one of the things we want to try out with you guys in this subject is whether you can actually visualize as future engineers how we can actually try and maximize the ability to reclaim at least parts or some parts of the building, and then always keep in mind that the that when the lifespan of the structure, design lifespan finishes with this, at least some part of that can be recovered and then reused. And then that is that is what we call the um, cycle economy. We are trying to visualize, uh, not to completely demolish and then make it as landfill. Rather, we like to see that is being thought about. For an example, car industry is doing this much better. Say, for an example, if you go to a wrecker or wrecking car yard, there are certain parts that you can reuse, so they can separate it. But in the construction industry, in the civil engineering industry, we never think like that. But there are some new ideas which are coming through to make this particular design for deconstruction philosophy coming through. So we have incorporated this aspect in your subject. So we like to see whether you visualize the building that you are designing now, and then the interior walls that you are thinking about, whether that uh, can be a smarter product than we used to do in permanent separation walls made out of cement and bricks and blockwork and things like that. Can we make it lighter? Always the lighterness means that the energy is less because the embodied volume is less. Um, so you can visualize in a residential perspective when you're doing your design whether you can utilize this knowledge into that. So um, and then the part of your particular assessment is also to ensure that some of you who are doing, there are 4 types of units that you are doing now. You must have been given, and then you all have already done your interior layout, I'm pretty sure. And then you must have had thought about this design for deconstruction aspects, trying to use the dry interior walls and think about the paneling system which you can use to optimize your design in that way. So we are also expecting your project to have um, tested, because every individual is using different interior layouts, what sort of flow, beam and the slab calculations that you would ended up making sure that the interior wall systems and the dead loads and live loads that you can be taken care of by the flow slab. So the flow slab design, your knowledge comes from the concrete structures subject. So you must have, I'm pretty sure you have studied concrete structures before, and then that particular knowledge can be put into this project. At the same time, you can have your own innovative and thinking how you actually plan your house at the same time. So I can explain that in 3 bubbles. So the aspect is interior layout design using. So you were given a certain space. This is pretty common in some parts of the world. Say, for an example, rather than you go into a residential, you're buying a residential building in a medium rise construction. Um, Most of the houses are look like the same, but in some cases, in the high end of that, what is happening is, say, you're taking the certain part of the floor slab, but the interior layout can be designed by yourself or by an architect for you. So it will be having a personal sort of a feel for it, like any other place that we're doing. I'm pretty sure in Hong Kong setting, it is not there yet, but there are a lot of high-end penthouses kind of things that they buy or they can hire part of a building floor slab, and then they can design the interior as they want. So the boundary, that is what we are trying to simulate in this particular project with you guys. So this has three or four important aspects which I have highlighted here. One is the whether your interior design suits the passive design principles which are applicable to Hong Kong situation. Can you, as an engineering student, use a set of principles, which we, in this particular case, passive design principles, and then do the design in such a way those principles are being executed, properly implemented within that space that you were given. That is one of the things. The other aspect is what we call your interior wall design and the facade. Of course, you're the outer walls and the interior walls of your design, whether it can be done through dry, what we call drywall construction. We used to do a lot of mortar, a lot of bricks plastered. That is how the interior partition was being done in most of the building, but it is no longer the case. It is different the way that we do, because some of the buildings will be re reused for different purposes. Say, for an example, you can have a situation where you have an office building, but after 20 years that particular property will be bought by some other investor and he wants to make it to a residential building. So therefore, in that type of situations, that they will be demolishing internal walls, non-load bearing internal walls, of course, and then try to reconfigure the interior. So this is happening everywhere. So we want our students to really, there are two types of design challenges we can give. One, this is a new one, there's no hindrance, there's no constraints, you can design whatever you want and you can build. That is one of the things. The other one is what we call the retrofitting, and then you have the building there and then the building will be changing, the occupancy will be changing. It was an office building previously, can be converted to a commercial building or a residential building. So for that reason, we are trying to see whether the design for the construction philosophy of your internal walls. So the main structure remains the same, columns, beams, and the core walls and the shear walls, that remains the same, but the interior will be slightly different. So that the interior non-load bearing partition walls should be designed for to be able to deconstruct or remove in parts like panels and then reuse it somewhere by somebody. So we also want you to utilize your engineering knowledge in this major third year design project. Your material codes you have used, say your Hong Kong reinforced concrete code or Australian one or Euro code, whatever that is, that your design codes and design knowledge of reinforced concrete we ask you to use it in a real project that you are undertaking. And then I am also doing another subject with you after this, the next year probably, that will be the long span and high rise structures. We the knowledge you are gaining here will be very useful to do that subject as well. So we are talking about here what we call design key performance indicators, which basically mean that we wanted to see whether your slab design, actually the optimum slab design, can we do it better, kind of a thing. So the optimization of your design, rather than you checking a beam for bending capacity and shear capacity, can you be smart about the structural configuration of the floor slab? So that is one of the parts in this one. And of course, there is a part that we measure in your final product, is the green building fundamentals have been utilized and then understood. So this particular subject is a major project-based subject, as you know by now. And then we are specifically looking at these passive design principles being utilized. Design for deconstruction philosophy is understood, and then you can actually exercise that a little bit, and as a graduate student. And then the other one is your flow slab will be can be designed. Of course, the slab design and the beam design, you have done it in concrete. Can you do it in a real life situation kind of thing? And then the third element is actually the green building fundamentals, which is being utilized in your in your uh, in your case. Um, your design will be assessed on meeting these particular factors 1 to 7. So I'm not going to necessarily read every one of the line. And then what this gives is a an understanding, an idea where to start and how you go about this particular project. My purpose of having this series of today's lecture and then tomorrow's workshop is for you to help you through to get to the final stages of the project as best as you can. So I have given summarized it in 7 dot points, guys. Basically, you have a very nice interior layout being designed, which you like, which makes sense, and then which has given a lot of thought about the interior design aspect of it. And then the second one is you your interior wall system is a smart system which allows you, if a future client acquire that one, to convert it to something else, or even the person who is residing there would like to retrofit or change the interior layout system, it can be demolished, it can be removed easily without a lot of generating a lot of construction waste. And then can you deconstruct it and then you reuse inside. So that is the idea we are looking for, where your internal wall system is actually can be removed, disassembled, rather than sort of permanently there and then demolish it. So disassemble and demolish is two different things, okay? The third one is, of course, the we like you to have your flow plate done, and flow framing. I mean, you must have done some examples in your other courses in concrete. For an example, you know how to design a beam and a slab and a column, but in this case, you have to actually develop your framing plan. You need to decide where the beams are. You need to decide where the which direction is the slab is spanning. So it is all under your control. We are not giving a particular span and asking you to design it. It's a mathematical exercise. But what we are asking here is actually, can you frame your flow and then get the best outcome for your design, and then which makes sense to you. So when you come tomorrow, that is the part that we will be doing. Pretty much, I'm helping you to see whether you can understand. Of course, this particular subject requires a little bit of an in-depth research. I'm pretty sure you must have already done it, both in sustainable features wise, passive design principles wise, interior paneling system design for deconstruction wise. You must be thinking about this topics as you're doing this design. You can, if you wanted to discuss about the carbon footprint, energy reduction, and then might as well, you can of course look for low embodied energy materials to use as your interior wall systems. And of course, you can talk about the smart appliances inside, the latest technologies, of particularly the window systems, double glazed most of the time nowadays, flow finishes, um, and then specific energy conservation apparatus, which is independent of the occupant. Like when you walk in, it is auto censored and the light will switch on. When you off the room, if you forget to switch off the light, it will automatically switch off, gauging that the occupant has left. So those type of modern advancements, which is very common now. If you wanted to get a good star rating to your building, of course, you require energy star rating. You require these type of smart thinking, smart gadgets, embodied energy being reduced, less carbon intensive material being used, reusing of this same material for disassemble and reuse, like in as I explained to you, like a spare parts of a car. That is how that industry will go forward. Um, I'm pretty sure you are halfway through. This is just a mark allocation. I'm pretty sure you have gone through this. I don't think that I need to go too much about it. It is just a matter of telling you. Uh, there are three aspects. I think assignment one is a design for deconstruction proposal kind of thing, and then the second one is the design aspect that you are doing now. And in the end of the semester, you will be having a poster presentation, which is allowed for about 20% marks. This is the final report. The rest. So I assume your first part has been already done by now. So here we are talking about what is passive design and what is passive design principles are. So we'll go through it very quickly, and pretty much has been on about 1 hour here. I'll take another 20 minutes and then we will have a break, so that you can follow from next. So we have given here some key points here actually. I have already spoken about it, so it is just to demarcate that we're talking about the passive design principles. So as I said, guys, the where I am is a little bit further down in Australia. Melbourne is somewhere up here. If you see my cursor, if I wanted to draw a little cross, so I'm roughly somewhere here. You guys are somewhere there. Now, depending on latitudes and longitudes, the weather conditions changes and then it reverses. All the passive design principles which are true, which can be used for the southern half of the planet, is not necessarily the same for the northern half of the planet. So the passive design principle is like a mirror image. So it is the mirror image. Say for an example, in Australia, we try to plan our house so the most of the daytime living will be spaces are facing north. But if you go to Canada, it will be the other way around. It is kind of in the same longitude and latitude, but you can see that it is if I go to Canada and if I design a home, I will look for most of the daytime living is located to the south boundary, south side boundary, and then in Australia it's the other way. So for you guys here, in your one is a little bit of a climate which is close to tropical. You have colder, relatively colder season. You are a little bit above, very similar to the Sydney condition, as you can see. Sorry, Sydney and Brisbane conditions. So basically, the point which we are raising here, if you are designing a particular building or a house, you have to think about what's the environment, what is the climatic condition of that, and then orient the building in such a way that the energy consumption is lesser. If you don't give a proper respect for the orientation of the building, what will happen is where which side I should provide my windows, large windows, which side is warmer side of my house, which is the cooler side of my house. Can I generate through cross ventilation a cooler side of windows having louvers which can open at the lower level, and then the warmer side of the house having louvers at the uh, upper half of the uh, height of the floor, so that a draft can be generated, a cooler, because cool air when coming through and then it's heated up inside your house, it will rise up, and then it will go from the top louver. And then if you that is what you call cross ventilation and draft being created inside the house. So there you can actually make that house very comfortable to live without air conditions. I know almost every household in Hong Kong has air conditions attached to them. So the point is that because I'm teaching it here, I wanted to be sure that you do understand which climatic condition in the Australian situation which is relevant to you. It is Brisbane and Sydney. So in Australia, we have these climatic zones very clearly identified. There are 8 climatic zones that we're talking about. So what your climatic zone is very close to zone 5, um, um, which warm and temperate condition. So it is an important aspect to know. So the set of rules are given in the document which is available to you. I'm pretty sure you will be using that zone and its climatic conditions to do your proper design. I have given here, I think about 12 dot points, which is Hong Kong has been really uh, using these principles in there, which is relevant to what we call warm and humid environments, which means that which is the Hong Kong situation. And if you look at the country which I come from originally, Sri Lanka, and then that also has a very similar weather condition to that of Hong Kong. But if you look at here in Melbourne, you hardly sweat, which means that the moisture content is in the atmosphere is very less. Say in your case, it's the humidity, which is about 80 to 90%, which means that the 8 to 9% of the vapor which that temperature can hold is being there. So relative humidity is fairly high. So these 12 points are the points which I like you guys to read carefully. It is very simple, easy explanation. Humidity is very high. That is why you're sweating most of the time. It is hot. Say, for an example, during uh, within daytime and nighttime, temperature variance is very small, few, but in Melbourne condition, it is quite high, other than in the summer period, peak of the summer period. Relative humidity high mean you'll be sweating and very uncomfortable. It dehydrates you a lot as well. Um, Cross ventilation cycle is the most effective. So actually speaking, if I to highlight this one, I would be the most important point for uh, this is this particular segment. I think this is That is the most effective strategy that you guys can do. So you can, one part of the house, windows must be openable. The cooler side of the house, if you have windows, can have lower lowers rather than upper lowers, and the summer hotter side can have the upper lowers, so that the cross ventilation can be really low. An interior layout of your house, because you are now designing, you can make sure that there are the doors and doors uh, effectively allowing that cross ventilation to go across your house, not go through a passage, not go through the corridor. You can actually really make sure that the cross ventilation not only serving one room to the one end of the house to the other end of the house, but it can actually really go across number of bedrooms and then get through it. It's a very interesting exercise if you do it properly. Um, yeah, so I have given some interesting ideas. Yeah, it is. I don't think that you can implement all of them, but use your interior layouts to justify. I know that most of you may have already done that. You halfway through drawing that, but at least you try and explain and describe what you are doing. So please have a look at those 12 dot points, which are very relevant to the Hong Kong situation. These are these have you have already seen. I'll brush through this. Okay, so the project induction is my next part of the lecture. So this will be a good point to have a small break. I will say it is now 5:23 um, from my side. You'll be 2 hours behind, so it will be 3:23. We will probably start at 3:45 from your end. From my end, um, we will it will be 5:45. So we will have a little bit of a break, and then I'll join you again in few minutes. So in this recording, there will be a 15 minutes lag. If I stop it now, then it will not be able to. We may not be able to record because I'm in the same class. So I will be recording this one throughout, and then there will be this 15 to 20 minutes gap will be there with this slide on. Okay. All right. I'll see you 3:45.